Continuing from our last chapter, today we're going to actually flip things around and start actually talking about functional programming and not so much about Kotlin as a language. So let's start with the basics. Let's start with fundamental principles and concepts. The first concept we're going to talk about are pure functions. What are pure functions? Pure functions are functions that don't have side effects. So let's think, for example, that we have a function with name sum, and it gets an first integer and a second integer, and returns also an integer. At this point, it's a function that basically can use those two parameters and give back a response. So in this case, it's a pure function because it's just taking decisions using uh, the the parameters that it receives, and it doesn't really affect any other instance. It doesn't really have a side effect. We can use it directly, and we know that there's no change on the instances that we have itself. This is a really simple function, but can this function become actually uh, not a pure function? The answer is yes. Imagine that by any chance we want to count the times that we've run this function, and we are going to have a counter. And inside this function, we're going to affect that counter uh, by incrementing it every time we call it. This is a side effect. Calling this function will affect something, an instance, a value, something that is not internal to this function. So if we do some here and say 1 plus 1, sorry, 1 and 1, we know that this is going to be return a 2. If we do sum of, again, 1 plus 1, this is again going to return 2. But if we do a print line, let's do that, and let's do the same here. We know that basically our counter is being affected by actually calling the sum function. That makes this function actually being pure. In any case, like our initial implementation, if this function doesn't have a side effect and our count still is 0, now it's actually a pure function. Let's go to our next concept. Our next concept is immutability. Immutability, it's about not having, again, side effects by not being able to actually modify the values of our abstractions. So, with this in mind, let's, for example, think about a data class that is a number that it's just going to be a wrapper for the ones that we have before. And let's say that this number has a num that is an integer, and we want this to be immutable. For that to be immutable, it needs to actually be a value. And we can actually go and say that now we're going to be using these numbers here, and this is going to return another number. So with this in mind, what's happening is that we're going to be adding or providing a value of number, and this is first dot num plus second dot num, and we're going to be giving numbers here also. Number and number. So why is this class really saying that something is immutable? Because we're using the keyword val, it's actually not going to be able to be modified. If this was a variable, this will be an mutable kind of instance. We could actually use a setter over that value. So for example, if I have a value first, sorry, value first, and I want to do first dot equal to, this is actually allowed. Even if I'm actually declaring that this instance will not change, I can mutate the internal value of the instance. So this actually breaks the intention of immutability. Immutability requires not only the current value to be immutable, but also the instances that it depends on to actually be immutable. Why is this actually something important? With this, you can validate by design that there's no side effects in your program. So for this, we're going to basically create that this is a value. And if this is a value, I will never be able to do this first num equal to. And now I'm ready with the immutability kind of principle. The next concept itself is referential transparency. Referential transparency, it's about not having side effects again. It's a simple concept but difficult to express. The intention is that if you replace the function by the value, it should always be the same without having actually the capability of having side effects. So, how does this translate into code? The same as we talked before. If this was a variable, uh, we even if this is a pure function, we cannot ensure that this is the same like this. If we replace uh, the value for the real value that is going to be uh, generated, we can actually not ensure that there's no side effect, there's no capability of this changing. Like for example, if another instance uh, is being called with the same first, it could actually be mutating the value because it's not immutable. And if this is running in parallel, we will never be able to validate that we're going to have the same result. It's a little bit of an unclear concept, but basically it shows the importance of having immutability and also having pure functions. So let's do a cleanup before continuing, and let's talk about the last but not least important concept itself. This last concept is that functions are a first class citizen and also that there's a higher order functions. What does a higher order function mean? Basically, the intention of this is saying that functions are treated as any other object itself. They can be passed as parameters, they can be returned as parameters. They actually work like any other abstraction. So let's, for example, generalize the sum function. to actually be a calculus function. So for this, let's say that we have a function that is calculate, and this is going to receive an first number. It's going to receive a second number, and it's going to return a number. Now, what we actually want is not to do the operation itself, but we want to be able to pass a function that will do the calculation. So this is going to be a function that gets actually passed to this other function as a first class citizen that is going to do the operation that we want. So we have right now an operation that is of this type. So we want to call that operation with our first and second value. So what's happening here is a function is being used as a first class citizen, and it's being applied to our first and second value. And with this, what we can actually go and do is that we're going to calculate a number one, and we go again and do exactly the same, our second number, and we at the end have to pass this function. So let's say that we have a and b, that both of them are numbers, and we do a dot num plus b dot num, and this is going to be our number. So this should actually allow us to create a number. So there seems to be a syntactical issue here, and the problem is, let me try to run it and see what happens. But the intention is this one. We are going to have a number, we are going to have whatever objects we want, but also a function. A function will not be discriminated by being something different. And function can be used as any other type of object. As you can see, if now we execute this, it actually works and it calculates what we expect. We could pass any other operation and we will still be able to actually execute. We might, for readability purposes, also want to pass the function that we implemented. So we can actually do that with using the two dots, and the name of the function. And we can actually pass that first class citizen function as a parameter. And again, it should continue working. As you can see, it makes code very predictable and very easy to read also. Now that these concepts are clear, let's start with some functional programming techniques. Let's remove everything that we have till now. Okay, so let's start now with some of the functional programming techniques. The first one that we're going to talk about is the functional composition. Functional composition is not about calling functions one after the other. Let me explain this in code. So we could have a value of our function one, and that is a lambda expression where we receive an end, and this returns a double. Uh, it's just the implementation of the value multiplied by 100, and we could have a second function that is having that double and returning a double. So let's say that is the, I don't know, 10 minus the iterator. We could say that composition is calling one function after the other. Like, let's say that we call our function 2 with the result of function 1. For example, this is not functional composition. Why? This is just only calling a function with the output of another one. Functional composition is more about generating a new function, a new abstraction that you can use for any case. So let's see an implementation of this. Okay, so let's implement the compose function. In our case, we're going to do this with an infix function that is going to have 3 different types. So A, B, and C. And this is going to be applied to functions that go from A to B. So when we call a function from another, then we have other function that we're going to call that is from B to the type of C. And then this is the outcome of all of this is really how we go from the function A to the function C. So let's then do the implementation, and the implementation is a return of other, using the other function to call the current instance with the iterator. Let's give it a try. So how can we call this? Basically, how we can call this is function 1 and function 2. If we do a print of this, should probably do exactly the same. So let's execute. And in reality, then the problem with this is we're not going to be calling this. We're not calling this with absolutely anything. So we'll need to call this with a value. So the result is exactly the same. The thing is, then what we're actually doing is we can do a function 1 and function 2 that is going to be equal to function to what we actually define here. And then we can actually reuse this function in general. So we can always call function one and function two wherever we actually want. So if we have a range of 1 to 10, we can always do a range.map of this function. And we have actually generated a new function that is a composition, a composite of the other two functions. And we could compose more and more functions one after the other to have reusable complex functions by themselves. That's the interest of actually doing function composition. That is actually not just calling one function after the other. The next technique that we're going to be looking at is currying. Currying is a technique to convert a function that takes multiple parameters into a set of functions, a sequence of functions that take a single parameter. What this allows you is to have a subset of functions that you can call in an iterative way with when you want to do multiple calculations with different values. So let's see an example of currying. For example, we're going to implement the sum function using curry. So we're going to have a value that is a function called add that is going to take an integer and it's going to it's going to return a function that gets an integer and returns actually an integer. How do we define this? So we define this as a lambda expression that returns a value, that returns another lambda that receives that value and does the adding, the sum. And now, with this in mind, we can have a val range that goes from 1 to 10. And from here, we can actually go and apply this range to the function itself. So let's say that we're going to do a print line of a range range.map of add of, let's say, 10, because our initial value that is going to be the a is going to be the 10. So with this in mind, we're going to call this again, and we're going to build, and we're going to execute. And with this in mind, we can see how if we start with 10 and we apply this over an array, we can see how it's actually adding the value as a second parameter that we're specifying to the result of the first parameter that we're actually passing. So this is an introduction to currying. In general, it can be used for more complex situations where you want to actually apply something that is the outcome of a different operation itself. Let's now talk about the next technique that most of us we already know. The technique it's called recursion. Rings a bell, no? Actually, this is a well-known way of breaking down a problem into smaller pieces. In recursion, the intent is that you can actually call the same function continuously to actually get some a value. So, but there's two different ways of recursion. Uh, there's head recursion. So imagine that we have an integer. Uh, sorry, we have a function that reserve that is a factorial function that gets an number that is an integer and it's going to return an integer. Uh, we could create a recursive function that basically returns whenever the number is equal to 1 and it either when it's equal to 1 it returns a 1 and if not it returns the number. Sorry, you can do this if this is a 1, if not else we return the number multiplied by the factorial of that number we have minus 1 uh, equal to 1. So with this in mind, we can already do a factorial of whatever we're actually of our range. So now we just need to call the factorial function with these two dots. That's why it wasn't compiling. And now we should be able to run it and we will see the factorial of those different values that we have on the range. What's the issue with head recursion? That is what we're currently doing right now. With head recursion, you have to maintain the state while you are doing those calculations because it needs to resolve the rest of the values of the in-depth uh, calculations to actually get the final value. So with that in mind, there's a second option that is called tail recursion, that the intent is to pass that state to the next calculation itself. So let's pass that result into the as a parameter. So now what's going to happen? Whenever we get to our last factorial, we're going to return actually the result. So we are not actually maintaining that state. And we're going to pass as a second parameter uh, that result multiplied by the number. So we're actually doing is actually passing as a parameter the factorial result. Now we need to modify our code to actually accept that range. So if we have a value here, we're going to call the factorial with that value and the initial value that is going to be 1. And now we're actually doing a map where we're actually giving an initial value and it's going to we're going to have uh, the same result. Recursion is not always the fastest solution, but it's a technique to solve complex problems. And tail recursion tends to allow you to have less possibilities of having memory issues. So last but not least, there's a last set of concepts and tools that we can use that are called monads and functors. In reality, You don't have to think too much about these ones because they are normally abstracted behind the language. It's interesting to know that most of these things come from category theory of mathematics, and a monad allows you to wrap a value, apply a set of transformations, and get the value back with all transformations applied to that value. With that in mind, you can see that that's what normally happens with most of the functions that we use. So we have flat maps, we have maps, we have reducers. Uh, all of those fall into the category of functors and monads in general. Each of them have their own transformation, their own value, and things like that. I'll let a link on the video so you can actually learn a little bit more about this category theory and how monads and functors work. But in any case, for our practical examples, there's nothing really that I can show you here. Just take in account that is something that it's important in functional programming, monads and functors. This concludes our chapter for today. Again, hope you enjoyed. As I said, there will be some links on the description of the video. Feel free to provide any feedback, questions. I'm open to have any conversations. Thanks, and hope to see you soon.